Alright, this is a cross-sectional view of the polysilicon resistor. You can see between the polysilicon resistor and the substrate, there is only a very thin gate oxide. So it really means that even though polysilicon resistor is almost the best for resistor on chip, however, you need to pay attention to such kind of parasitic capacitance because, again, it is very close to the substrate. But how to simulate such kind of parasitic? Actually, according to SPICE model, it will be much more complicated even than this. It means that for our SPICE, actually, the resistor will be divided into quite many sub-resistors, right? And in between, you will have a lot of parasitic capacitance. That's it. That is the way we try to simulate the most accurate result. However, nothing is free. You need to pay for it. Pay what? Time for simulation. This is the reason why for your especially poster simulation, you need to spend a lot of time for that. Sorry for that. According to accuracy, we need to pay time. And then, for resistor layout, if you would like to, how can I say, to get the largest resistance, maybe you think such kind of serpentine layout will be good for you, right? However, according to accuracy, I strongly not recommend it. Don't do it. Even need high resistance, do something like this. Okay? Then connect them in series. Oh, connect here, connect there. Yeah. In this way, you can achieve the resistor with much accurate resistance. And I told you already, what is the actual length for resistor? It is from here to there, right? We don't care the accuracy here, the accuracy there, because they won't be counted. And in this way, you don't need to have such kind of dummy. That is too much. We only care about what? We only care about the actual width. So to prevent, how can I say, side action, right? At the boundary, we need this dummy and that dummy. Good enough, good enough. Don't do any kind of over design and over layout. No, sorry for that. We dislike over design. We also dislike over layout. These are over layout for dummy. Okay, don't do it, please. Don't waste your time and money. Then, this is some kind of interdiscretization layout for the resistor. Yeah, you need to mix them up. That's it. To achieve better matching. That's it. All right. And from the very beginning, I told you we need to use such kind of unit device for layout. So, for example, this is 100 ohms. You need 200, then 2 in series. Don't simply make it longer, 2 times longer. No. That is no good for matching. Okay? Yeah, exactly here. How about 5 ohms? 500 ohms, just 5 unit resistors connected in series. And again, consider about the dummy. Actually, on this page, nothing is good. Nothing is totally correct. Anyway, that is reprinted from Professor Hong Yi Huang's lecture notes. But why? There's nothing totally correct. I still have this for you. I would like to warn you. For example, this and that, no good. Why? Serpentine layout. Moments ago I just told you, serpentine layout, according to accuracy, is totally no good. Right? Since it's not accurate, tell me why you still would like to have such kind of dummy. Ridiculous. Itself is inaccurate, sorry. So never mind how hard you try, you have such kind of very strange shape for dummy. Sorry for that. Itself, the main body of the resistor is inaccurate. So never mind how hard you try, it is still inaccurate. So please don't touch. And how about this? What's going wrong? Again, no four-sided dummy for resistor, right? Keep this in mind. Don't make any error the others would like to make. No, that is not for my students, please. Okay? And this, beautiful. Again, reprinted from Professor Hong Yuan's lecture notes. What's going wrong? If you would like really match both, then 1 to 1 to 1 to 1 to 1 to, that is ridiculous. Okay? Because the first golden rule is common centroid. Without common centroid, you cannot make anything. Right? So it is only beautiful but useless. OK 哈，四個無內容嘅物件，一定要講重心啦哈。Yeah. Anyway, for resistor, if you would like, resistor is some kind of how can I say dirty? I need to say noisy device because according to the current conduction, usually the electrons need to collide with the crystal, with the lattice. It will generate a lot of noise. According to this kind of noisy device, you had better use such kind of guardrail, okay, to limit the noise it generated. However, the noise can run not only in all those four directions, but it can also go up or go down, right? Upward and downward. So what you can do, especially for downward, it should be, there must be a substrate. We hope you don't interrupt, you don't interfere the substrate too much. What you can do, some kind of shield below the noisy resistor. Unless it use something like this hose, P-type, okay, then it will become much less noisy. Maybe you can also forget all those guardrail and the bottom plate for shielding. But usually you will use N-type, right? Then, sorry for that. It is noisy. Keep this in mind. So, this is what I would like to share with you. However, moments later, I will show you even better plots for explanation. Then, concentrate. Oh, finally, Professor Hong Yuan's students did something good. Yeah, not only beautiful, but useful. See? 1, 2, 2, 1, 2, 1, 1, 2. Bingo, that's it. Then, two-sided dummy layout instead of four. Bingo, surrounded by guardrail. Very good. If you would like to make it even better, then again, to the bottom of the resistors, you need to have some kind of shielding plate. Later I will show you how to make it. Alright? If you would like to make it better, this is for second order according to the previous chapter, chapter 6, right? To the end of chapter 6. Yeah. I show you one of the best papers from Professor Geiger's lab. How to do such kind of common centroid, blah, blah, blah. Okay. Yeah, anyway, 1, 2, 2, 1, right? How to flip it horizontally, vertically, with symmetry or anti-symmetry. Yeah. The only rule is the newly generated block needs to be different from the original one. That is what I require you to do. Okay? Anyway, symmetry and anti-symmetry, both are very useful. Don't only focus on symmetry. Alright? If you have this, so you can see this is already the second order gradient cancellation. How to make it to be third order? This is no good because here for second order flip to the right. It is not right. It is wrong. Right? Why? Because the newly generated block is exactly the same. If you shift it back to be fully overlapped with the original one, you will see they are exactly the same. Then the power of cancellation is still the same. The second order I mean. Alright? So here you can see again, don't focus on symmetry only. Here you need anti-symmetry. 1 becomes 2, 2 becomes 1. Okay? That's it. Here is what I would like to share with you. How to do the best shielding for resistor. We wouldn't like to protect it. Why? Because it is noisy. We would like to protect the others besides resistor. Okay? How to do it? How to make it? Here you can see for polysilicon. What kind of shielding you can have? If you have P substrate, okay, then you need to have N well. And here, on the top, it is N substrate. So they have P well for you. Alright? Anyhow, it is, how can I say? It is not so bad, but I cannot say it is good. Why? According to the well, the resistivity is quite high. So if it generates any kind of noise downward, how can the P well absorb all those noise for you? It's really hard. According to the large high resistivity. Okay? To make it better, we need to increase the conductivity for such kind of shielding plate. Then you may think, okay, I have such kind of P plus diffusion. Here again, that is P substrate N well, see? And then on the top of the N well, we can have such kind of P plus diffusion, right? Because P plus means the conductivity is much, much better than N minus. It is good. It is good. But you will see, here we have poly 1. Why not poly? We have poly 2. Why not poly 1? Why not poly 1? Here is poly 1. Okay. And why, for the second, use poly 2 instead of poly 1? Any idea? According to the second chapter for manufacturing process, I told you, for such kind of polygate, I mean poly1, right? It needs to be fabricated earlier than your source and drain. P plus or N plus means the source or drain for your MOS, for your PMOS. Got it? So if you use poly1, sorry for that. It will be fabricated earlier than P plus or N plus. It means you don't have the chance to have P plus diffusion beneath the poly1 resistor. Sorry for that. No. Okay? If this is the poly1, I mean you lower it to become poly1, then it will fully cover the channel area. Here will become channel area. There will become source and drain areas. Okay? So it means, sorry for that, you won't have this area diffused to be P plus. No, sorry for that. Totally impossible. Okay? If you would like to have the whole area become P plus doping, you need to use poly2. But you may argue that for my process, I don't have poly2. That is for old processes. To my memory, anyway, older than 0.35 micron process. Okay? For this one or for earlier processes, yep, you have double poly. 2P for what? With capacitor. Okay? In the past, nowadays, what kind of capacitor you usually use? MIM. And then MUM. But both didn't exist. Yeah. For more than, I guess this one, almost more than 20 years ago, 2 decades ago. So for that, they don't have such kind of good capacitor. What TSMC, UMC can help? Double poly. Poly1 and poly2. Okay? That is the difference. Nowadays, I don't think you have any kind of process with double poly unless you go back to use 0.35 micron process. Otherwise, totally impossible. You have single poly. For example, how about 0.80 micron? We call it 1P6M. It means single poly, then 6 metal layers. And how about 0.35? We call it 2P4M. Okay, double poly and 4 metal layers. According to the naming of the process, you will know how many layers for poly, how many layers for metal. Okay? Yeah, let's go further. This is already very good. If you would like to make it even better, you can have not only shielding here, okay, to surround the resistor with that ring, but also the bottom plate and the top plate to make it even better. All right? Anyway, this is not impossible, but usually we don't do such kind of layout too much. Yeah. To the top, usually we don't care. Unless it is really noisy, just like inductor. But for inductor, it usually don't have the possibility because we use the top poly for inductor. Okay? So, to be honest, No, you can make it. You can do it. It is not impossible, but too much. That is my comment. You can do it, but usually we don't because we simply don't care. Such kind of noise upward because usually nothing there. Okay, maybe only wires, but for wires we have a lot of parasites, so don't care. Wires are only some kind of supporting device. Okay, they are not device at all. They only help us to support the operation of our main devices. So anyway, why downward noise is much worse? Simply because P substrate. And the noise, if it interferes the operation of the P substrate, then yeah, everybody will get the impact. Okay, because all the devices share the same substrate. That's it. All right? Do you need double gathering? Usually not. Usually not. That is also some kind of overlay out for resistor. Okay? Maybe for inductor, it is really, really noisy. You can apply it. But for resistor, forget about it. And again, for the first time, I mentioned such kind of double gathering. I told you, one is truly useful. The other one is not so useful. All right. So for P substrate, what kind of double ring, P type or N type, will be truly useful? P type, P plus. Okay. If you insist to have N type, please put it into N well. Alright, because according to the cross-sectional view, N plus here, N well there, it can help you to stop horizontal noise for such deep. How deep? The depth of N well. Okay, that's it. Again, if you would like to enlarge the resistance, then you can consider dog bone, 狗骨头式的. Why? Because you can reduce the W to the minimum. Okay? It is totally possible. Yeah, and then again connect them in series to enhance the resistivity even further. However, serpentine is usually the one I wouldn't like to recommend because it is not accurate. Alright. We can go further. Laser trimming. It is used in the past. Nowadays, forget about it. Okay? Because it is too expensive, to be honest. And after laser trimming, sometimes it would go wrong again. That is what the two main reasons we wouldn't like to apply it nowadays. But the concept is still good. Alright? So allow me to tell you how to do such kind of laser trimming. Very expensive one. You need to measure it. For example, this is some kind of resistor before trimming. Okay, then you need to measure it, and this is the reason why you need the so-called test pads or probing pads. You need to use your probes here and there to measure the resistance, to check how long it is. I mean, how small the resistance is, then according to your target, you need to enlarge it. How can you enlarge it? You can see here. See? It means what? This is for laser trimming. You just use your laser to cut it, okay, to burn it. So in theory, the effective width will become here instead of there, right? So the resistivity will be reduced. Got it? So in this way, we can increase the resistivity, the resistance. All right? This is another example. Yeah, again, from the beginning, this is the width. Then you cut it to make it become smaller. Yeah, to enlarge the resistance. Anyhow, it means what? From the very beginning, the resistance you laid out should be smaller than the target value. If after fabrication it is already larger, then you can do nothing. Okay? And how about the other type? Yeah, they have such kind of loop type. Many kind of loops connected in series. So you have more flexibility to cut it. Okay? You can cut here or cut there. I feel like I don't care. Alright? It depends again on the true resistance you measure. After that, you can make the decision how to do such kind of cut according to laser trims. Okay? Yeah, anyway. So the idea is still good. You need to measure it first and then make the decision how to do calibration. But nowadays, according to calibration, we seldom use, we almost don't use any kind of laser trimming. Alright? It is very expensive. And why? Sometimes it would go wrong because for such kind of laser trimming, you try to use the high energy laser to vaporize this area and that area. But after that, you need to cool it down. Then sometimes it is not what you think. Okay? The vapor, maybe they will, after cool down, they will stay here or there to partially connect this area and that area. It is really no good. Right? 用雷射去烧它的话，有些时候它不会完全气化掉，那你烧完之后降温，它有可能又粘结在那个附近，那部分的又把它连在一起了。That is really bad. Okay, so forget about it. Allow me to show you some of the technology for calibration, for resistor adjustment. Usually we call it calibration, okay, instead of adjustment. For example, for our lithium battery, for different compound, you need different protection voltage. For example, for overcharging protection, 过充保护. Usually, the protection voltage is around, to my memory, 4.2 something. Okay, but 4 definitely the same. Okay, but 2 something. It depends on the chemical compound. 不同的锂化合物所要求的这个电压是不太一样的。That is really upset. It means for such kind of very cheap lithium battery charger, you need to have tens of or even hundreds of overcharging voltages for your customers. Okay? So it will be really expensive for such kind of fabrication. Yeah. For customer A, you have, right? For customer B, right? For customer C, wow. How can you do such kind of, how can I say? You need to, you need to ship the correct voltage to the correct customer. So it will make your fabrication really, really complicated. Okay? There's one way, just like this, with some kind of variable resistor. That is the idea. Hey, if I can vary the resistance, then I can please all my customers. Right? One for all. Only one charger for all the customers. But you need to make sure you can generate many kind of voltages to protect their lithium batteries. How can you do that? With the help of variable resistor. Wow, it's piece of cake. But what is the problem? Hey, our circuit is called solid state circuit. That is for IC, right? Solid means it's just like the stone, the rock. It is solid. It is really hard. So it is no way for you to move the contact, right? After fabrication, no. So it means what? To adjust the contact, you need to make it before fabrication. Wow. So it is some kind of dilemma, right? How can you make it? How can you vary the resistance? It should be before the end of fabrication. So anyhow, for each process, it takes 20 to 30 something steps or masks. All right. So it means what? You have, if you are lucky, you use top metal for such kind of VR. Okay, you can finish all the steps except for the last one. And that's it. So when you get the order, I know 4.2 something, right? Then I can make the decision where to locate the contact for the top metal. Then you ask your manufacturer to finish the last step for you. That's it. Okay? So you can keep from the beginning. You can get help from your manufacturer to produce a lot of a lot of wafers. Okay? Except for the last step. That's it. So whenever you get the real order from your customer, you make the decision for the position of the contact, then ask your manufacturer to finish the last step or last steps. Anyway, this TSMC wouldn't like to help you. That is some kind of dirty business, too troublesome. Okay? It means what? Only the medium or even only the small scale producer, they would like to help. And this means what? Maybe you need to focus on 6-inch wafer for such kind of production. Okay? And also, how to keep all those unfinished wafers not in the air, because oxygen will have a lot of oxidation to kill the performance. So you need to put all those unfinished wafers into some kind of closet with a fully filled with nitride.
用氮气整个把它充满那个柜子啊不，你的半成品立刻就被氧化掉了，完全不能用。Okay, that is the logic thinking for VR, and TSMC, UMC, they wouldn't like to help. We need to go for the other small scale producers. Yeah. So again, the length is from here to there. You can change this one to make the length longer or shorter, to change the real resistance. Okay. And the other one we call it fuse, 保险丝哦。Okay. If you need it, you keep it. If you don't need it, you burn it out. How can you burn it? Again, you need such kind of trimming pads. Okay. So after, if you would like to burn it, then you use your probes to touch it with high current to burn it. Alright, but the problem is even worse than laser trimming. After the high current for burning, you need to cool it down, and again, it may partially reconnected again here or there. Alright? So nowadays, nobody would like to do any kind of fuse. But what we can do? With flash memory. 用快闪记忆体。Okay? But only one time programmable OTP. One time instead of multiple time. Usually the flash memory you are using, they are MTP. They can be programmed for not only multiple times, no, thousands or tens of thousands times. But for such kind of calibration, usually we use OTP because OTP is much less inexpensive than MTP flash. Okay? 只能烧一次的快闪记忆体跟可以重复烧入的那个价格差非常的多。Anyway, for TSMC, UMC, they would like to provide you such kind of IP for not only flash memory, even for DRAM, SRAM, blah blah blah, all of them. But if you license their flash memory or DRAM, blah blah blah, okay, you need to pay much more. Because according to cost performance ratio, you cannot compete with the flash memory producer or DRAM producer, just like Samsung. Okay? Such kind of on-chip you license from TSMC, the CP value is much lower than Samsung's. So only for, how can I say, a few bits, a few bytes, good enough. Don't mention about gigabytes. Sorry for that. Yeah, even for megabytes, you need to think about it, rethink. Would you like to pay such kind of big area, much larger area than Samsung's? Okay, only for very few bits will be good. Yeah, for such kind of on-chip memory application. Okay? The best application, I guess, is for calibration. We hate it. Never mind you use fuse or laser trimming. They are expensive and troublesome. Okay? Then how to make it even useful with less cost? Memory, flash memory. Okay? So, for example, this is something you would like to do calibration to make the final resistance becomes what you want. All right? A very good example is for termination. Terminator usually needs exactly 50 ohms. Okay? How can you fabricate it? How can you fabricate such kind of resistor with exactly 50 ohms? No way, no way. Yeah, for accuracy, for absolute accuracy, you need to tolerate tens of percent in accuracy, okay? In error. So you need to do such kind of trimming or calibration to make the final value exactly the same as what you need. How to make it? This is a very good way. So from the very beginning, again, you need to measure the main resistor. So and here usually maybe to VDD or to something. And to VDD, you have VDD pad, right? So you can set one pad, one probing pad. Probing pad usually is quite large. They are area wasting. So you can set, if you need to, for example, here is to VDD, there is to ground. Congratulations. You don't need extra probing pad here, probing pad there. No. You can simply use the VDD pads and the ground pads. Okay, save 2 pads means a lot of money. Okay, and then the process is after measurement, the real value for Rx. Then you will know, and how much left you need to have. That's it. Okay? Because they are fabricated at the same time. For example, if you have 40 here, then it means you need 10 more, right? And you have such kind of, usually, minorly weighted resistor array for calibration. Now, 1 to 2 to 4, you can, with very simple calculation, you will know which one needs to be left, which one needs to be shorted. Okay? So, in the past, if you need it, you need to open it. Burn the fuse here. Okay? If you don't need it, you would like to short it, how can you make it? You just let F2 there. Don't touch. It will be shorted. That's it. But nowadays, we don't do such kind of silly fuse. Okay? Yeah, you simply have some kind of analog switch. Transmission gate, I mean. Okay. Bingo. Then how to turn it on or off? Very simple. Again, with the help of flash. So after measurement, you can make the decision to make it on or off, then store the calibration value into flash memory to keep on and off state for all those calibration resistors. Bingo, that's it. Very simple idea, right? That is the current methodology to deal with calibration. And this is the reason why TSMC, UMC would like to provide you such kind of on-chip flash. To my memory, TSMC didn't design such kind of on-chip flash for you. They also licensed from the other designer, then provided such kind of service. And in between, they can make some more money. That's it. Okay? If they get 10, maybe they will sell you 20, right? That's it. That is business. This is for resistor connected in series. You can make it similarly for them connected in parallel. The same, okay? Similarly, not the same. Just do it by yourself. So for matching requirement, if you would like to have such kind of minimum matching, oh, calculate. Hello. For minimum matching, usually just like this, positive, negative 1% for 3 sigma matching. Okay, it means 6 to 7 bits resolution. Yeah, anyway, that is only good for base network. Alright? For your real circuit, you need at least a moderate matching. Yeah. You need to enhance the accuracy by 1 order from 1% to positive negative 0.1%. So it is around 10 bits in accuracy. Yeah. It is good for your band gap reference, op-amp, comparator, blah, 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 blah. All right. So how can you make it by not only interdigitization, but common-centric layout? Yeah, hopefully at least second order. Okay? For precise matching, it's really hard. Usually, you cannot make it with layout itself. No, usually with calibration. Okay? So the guidelines for resistor matching are here. Read them by yourself. Okay? Do it by yourself. Because for all those details, I told you already for chapter 2, right? To the end of chapter 2. Yeah, that is some kind of general rules. Just follow it. Okay. On this page, I would like to explain something according to IR drop. Here. Yeah. It is a very important concept. We call it IR drop. But what is IR drop? You can see that is the VDD and ground of chip. Okay? Then, that is a cold circuit, and you will have a lot of I/O pads, right? Then you need bonding wire to the outer space. No, to the outside world for VDD, and the other pad to the ground. Okay? Yeah. New engineers always think, oh, if I provide 1.8 volt here, 0 there, then my chip will be powered totally by 1.8 volts to the circuit. Is it possible? No. Totally impossible. Why? Because the bonding wires here and there, they have some kind of resistivity. Okay? Yeah, even worse is not bonding wire. Even worse is the wire from the I/O pad, okay, to your real circuit in the middle, right? So from the VDD pad to your core circuit, from the ground pad to your circuit, usually you need to use metal line for routing, to route a long way. Okay? If you have your chips taped out, you will know what I'm talking about. After you finish the layout for your core circuit here, you have a lot of I/O pads, right? Then you need to, for your VDD ground and I/O pins, blah, 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 blah. I'm talking about the routing here and the routing there from your core circuit to the VDD and ground pads. They need to route a long way for you. Okay? it will induce a lot of parasitic resistance. In addition to the bonding wires. Yeah, think about it. So it really means what? VDD and the ground of chip. And then your real circuit, you have your VDD prime and ground prime. They are not the same. Okay? According to the current flow, it will flow in this way, then through your core circuit, then back to the outside world. For such kind of resistor here, according to V equals IR. Got it? That is what you learned from your senior high school for fundamental physics. IR means what? The voltage difference according to the parasitic arc. Okay? So it means what? Sorry for that. VDD prime equals VDD minus IR. Got it? You have IR here, you have IR there. Don't be too happy. Those two IR will cancel each other. No, sorry for that. There will be summed up. Okay, because you have 0 here, and according to current flow, you minus IR to be here. But you 8 IR to be there. So from 0 to there, right? Okay? So what is the difference? Sorry for that. The final result is VDD minus IR and the other IR. All those two R's are not the same. Okay, maybe IR and IR prime. This is for VDD IR and that is for ground IR. Sorry for that. It means the real VDD and ground here, according to IR drop, it is lowered from VDD but upward from ground. So it means what? The real supply voltage is less than you think. Okay? In this way, there are many kind of drawbacks. First of all, you waste a lot of power here and there. Right? Because P equals I square R. Right? Sorry for that. The more resistance means the more power you waste here and there. Not all the power, not 100% of power is consumed by your core circuit. Sorry for that. Maybe you think, there is no much resistance here. That is what you think, but it's not true. For our big chip nowadays, how much is the current? The peak is around here. Okay? I'm not kidding. I'm telling you the truth. I'm not telling you 100 milliamperes. No. Sorry for that. No milli at all. Yeah. Hundreds of amperes need to be consumed by current big chip. Just like our iPhone. They are power-hungry monster. Okay, for peak value, they consume hundreds of amperes. Okay, so think about it. Even you have maybe only, right? For both, sum them up. Not a big deal, right? Sorry for that. You need to waste a lot of, not 10 watts. No, sorry for that, not 10 watts. Because the square root of 100 by this one, it will cause you a big problem. Okay? So usually, you need to make it mini ohms. Quite small. Even it is mini ohms, the square of 100 still means that you need to consume around 10 watts. Even for IR drop. Wow! How many 10 watts you can have for your mobile phone? Not too much, right? That is a big problem, not a small one. Sorry for that. It means you need to try your very best to reduce such kind of IR drop. Okay? Otherwise, they will waste a lot of power for you. It is no good. It is no good. Okay, let's go further. How about the other problems? That is originally what you think. Your VDD here, your ground there, but finally it is reduced to here. It is increased to there. So the operation range, according to voltage, is smaller than what you think. And it really means that the noise margin is also reduced. Okay? Noise margin in theory is in the middle of your VDD and ground. Right? So the noise margin will reduce from here to there. Got it? So it means what? Your circuit cannot tolerate so much noise as you imagine from the beginning. Sorry for that. Okay? Even for digital circuit, the possibility of going wrong will be substantially increased according to the reduction of noise margin. Okay? Nothing is perfect. Anyway, we have a lot of troubles. Power consumption, noise margin, blah, blah, blah. So, again, try your very best to reduce the resistance. Okay? But how? First of all, core circuit. VDD pad, ground pad, right? For large chip, single means not enough at all. And how many you need? Hundreds. Okay? You need to have hundreds of VDD and ground pads. It means all of them were effectively connected in parallel. Because all of them with bonding wires to the outside VDD, of chip VDD, of chip ground. Okay? And then, how to connect the I/O pads to your core circuit? That is another story. Later I will show you.